All right, cool. Hey, thanks. Hey, everyone. So I'll be talking about zero-knowledge proofs and Web3 and Mina Protocol. So let's just get into it. I'm one of the co-founders of Mina. I currently am CEO of the Mina Foundation. Here's what we're going to talk about. First, I think it's good to just kind of zoom out for a second and just think about Web2, Web3. What is the advantages? What are we bringing to the table here? We'll also then talk about zero-knowledge proofs themselves. Like, what really is a zero-knowledge proof? We've heard about them already today for zk-EVMs, but they're really a much more powerful general-purpose cryptographic instruction than just that. We'll talk about how you can start building with zero-knowledge proofs and zk apps, and particularly Mina's architecture that makes that possible. We'll talk about SnarkyJS, Mina's TypeScript programming language. It just is TypeScript. It's like a library for building zk apps. And then we'll talk about where to learn more, including there's going to be a live coding with zk apps and SnarkyJS tomorrow here at 9 a.m. So come back for that if you want to just start building with this stuff. More of an intro. So just zooming out for a second, I think it's important to think about where we are today with Web 2, what Web 3 might be able to accomplish, where we were originally with Web 1. And I think if we look at things, it's pretty clear, originally things were very kind of user-centric, user-owned, but kind of onerous because of that. And quickly that became a place where there was so much advantage for the user experience and the way to build out applications with building centralized products and services that became Web 2. And now we're in this place where, okay, there was probably some ways to improve on that, and we're back at Web 3 where we can probably improve upon some of the centralized aspects of Web 2 and make something that's more user-owned and more user-respecting and different model for how we can build these kinds of applications in general. There's two particular properties that zero-knowledge proofs are very important and related to. Both privacy and verified computation. So I think it's just good to take a second to remember why these are useful. If we want to build feature-complete, user-respecting applications, we probably need privacy. There's lots of applications that want to work with sensitive data, and you just can't build them without privacy. As well as lots of applications where you probably also just don't want to be exposing all that sensitive data because you want to respect users and you don't want to just put all their stuff out there for anyone to see as part of them using your application. We also have verified computation. We have this property of decentralization, this property that everyone knows what's going on and can verify and can check and authenticate and make sure that the system is working as expected. And for that, verified computation becomes extremely important, whether that's checking all the blocks in a blockchain or whether that's using something like zero-knowledge proofs. So, zero-knowledge proofs. These are this cryptographic object that let you have a program, and I can prove to you what the output of that program is without revealing all the details of the inputs that I gave to the program, and with you being able to check the output very, very quickly, much faster often than if you had run the program yourself, because we can make a proof of huge amounts of information and computation data and put that into a single quickly checkable proof. So this has a lot of useful use cases. So you can build zk-Rollups with this, both app-specific zk-Rollups, zk app chains, and zk-EVMs. You can do private transactions with this. You can do private voting with this. You can do private identity things with this. And you can also just verify large computations in general. zk-ML is one thing where you can verify the outputs of large neural networks being explored right now in that domain. So there's all these kind of cool properties that you get from these zero-knowledge proofs. And you can see these are pretty useful if you actually want to build a Web3 application that uses privacy, that has large amounts of compute. By pulling in all these properties, you get to be able to actually do those things. So I think it's also helpful to just pause for a second and say, what even is what is the API for a zero-knowledge proof? This is how I usually think about zero-knowledge proofs, kind of in the abstract. Is really they're just an API. It's the same as any other cryptographic object. You have a hash function. You give it a string. It gives you another string that is hashed. You have public key signatures. It's a family of 2 functions now. You can sign something and you get a signature. You can then verify that the signature actually came from the public key, created with the private key that corresponds to that public key. Zero-knowledge proofs are just another, kind of same idea in this set of ideas. Now we have 3 programs. One, you actually give a whole computer program to. So you give, in some form, we're not going to go into in detail, but in some mathematicized form, your program. And it compiles that into a fixed size verification string, verification key. You can then, as a prover, prove that if you run the program with a set of public inputs and private inputs, the program outputs, yeah, true, that was like, called the program in a way that was valid. And someone else can come along and then verify that if I was to have called that program with the public inputs and some hidden private inputs that I don't actually get to see, that it actually will verify to true that actually the program said that those were valid inputs and public and private inputs. What's really cool about this is it does take a while to actually create the proof, but you can often create the proofs in parallel using some techniques. And then you can also verify in O of 1 like constant time. So I can make a proof of hundreds of gigabytes information, many compute hours or days of compute, and then you can check it in like a millisecond using this really quick verification technique that zero knowledge proofs have. So that's like super cool on that side. And also you have these things on private inputs. The program can say, I want to make sure your private input is signed by this authority that I trust, plus the number that was signed is greater than 18, showing that you are older than 18. And the private input that, my exact age doesn't make it into the proof that's being verified later. Computer goes to sleep. But still, as a verifier, you know that that was actually part of the private input, that the private input was greater than 18. So I think if you're like programming, then this is like a good mental model to have in mind for what's actually going on. So Mina is this layer 1 that is built on zero knowledge proofs. It has a couple of cool things about that. For one, the smart contract language is zero knowledge proofs. Everything you make in the smart contracting language is always being compiled down to a zero knowledge proof. And because of that, the programming language for it, SnarkyJS, has native functionality for privacy, native functionality for large amounts of compute, and other properties like recursion we'll go into in a second. Mina also has this property that the whole thing is a zero knowledge proof, in that every time a block is added to Mina, really what's happening is it's updating a zero knowledge proof of Mina. And so you can actually verify all of Mina, consensus information, and the actual transactions, including smart contracts, in a single zero knowledge proof that's very, very small and easy to check. This has a couple cool outcomes. For one, it means that you can verify Mina on phones and browsers, wherever, as you would with a full node, but in only a few kilobytes of information. But also, it means that we have very good interoperability with other chains, because you can then verify Mina inside of a smart contract running on another platform. And there's a lot of work going on right now to put that Mina proof on top of EVM on Ethereum in particular, so that you can program with ZK apps and get access to the privacy and the verifiability technology, and then bring that over to Ethereum. So if you're building a Web3 application on Ethereum, you can still get access to native privacy and scalable verifiability through zero knowledge proofs on Mina through this like very secure bridging. Some more like kind of dive in the details on these things. So ZK apps are just Mina's smart contracts. We have an example on the top right that just is TypeScript, but it's an example that is going to get compiled down to a lot of cryptographic proof that then will correspond to a verification key for the program. It's general purpose. This isn't just like zk-EVM. You could build a virtual machine using this technology, but it's really a kind of a step back to doing general purpose things with zero knowledge proofs, like privacy, like scalable verification. It's also all written in TypeScript, which is very cool. It's not like TypeScript-like, it just is TypeScript. You can stick with all of the tooling you like, all your, it has really good for Visual Studio we'll go through later, as well as NPM and all that stuff. And so, it's very easy to get started with and use. It also, this is a little under the hood, but it has full support for zero knowledge proof recursion and composability. These are like kind of more advanced features of zero knowledge proofs in these kinds of systems, but the way Mina's proof system is designed is that you can have zero knowledge proofs that verify each other. Key to both how Mina itself is succinct and easy to verify, but also very useful if you're trying to build a zk-Rollup or construct a lot of proofs in parallel that then get merged up together, and you can achieve some cool scalability properties that way. It's also powered by this open source proof system that O1 Labs, one of the Mina ecosystem companies, has developed, called Kimchi, which is like a very powerful proof system in general. So I mentioned before in this briefly, what Mina's doing is every time you make a block, it updates a recursive zero knowledge proof that says the previous blockchain was valid, And when I add on this new block, the new transition information matches the correct program it's supposed to, and it matches, it verifies out with all the inputs and outputs match up, all the consensus information is correct, et cetera, and extends the blockchain that way, where still the proof itself is very small and succinct and size, but it goes back all the way to Genesis through the recursion. And yeah, it gives you this phone-lib verifiability on both phones and browsers, and it also gives you this very secure ZK bridging, which is cool because then you can do the ZK app thing I mentioned earlier. Okay, so let's dive in a little bit deeper now to Mina and ZK apps. So first, let's just take a look at what even EVM is doing on Ethereum. You have some EVM code. It lives on chain. It has some gas associated with it. You call that function, and all the nodes on the Ethereum network evaluate calling that EVM code with the input you gave it. So this is every node of the network runs the function, which means you have gas, which means that because you have to actually share the information, it's not necessarily private. Alternatively, what ZK apps does is you instead share a proof of a zero-knowledge proof program, and then all the nodes on the network don't actually run that program. They just check to make sure that what you've provided, the proof you've provided, verifies with respect to the verification key on chain that you are attempting to call. So this is pretty cool because, again, you have that privacy property. Your proof can hide in pieces of information about the underlying program call you made. There's no gas because the proofs are the same size to check every single time. You get the composability, so you can have atomic transactions where ZK apps are all calling each other. And we have some cool scaling properties because you can construct these zk-Rollups in parallel to the main chain and then commit the results of those zk-Rollups back. And it's all you don't have to be a cryptographer to do that. You just use the TypeScript language to build your zk-Rollup. And you also get this cool interoperability. We want Mina zero-knowledge proofs to be something that is useful and available to Ethereum and is able to be something that people that are building awesome applications can then pull in all this great privacy and scalable verification stuff when they're building their application. It's not out yet, but there's a tutorial going on exactly how to do that so that to make it super easy to do this cross-chain stuff. So here's a very simple proof of what you can do with this. It's very specific. Let's say I prove I want to have greater than $100 on bank account, and I don't want to reveal the exact amount or any other information about me. I can then construct a proof, and that proof can be brought on chain to Mina and check to make sure it verifies with respect to the verification key of the program that's actually doing the logic around this check, and then that can be bridged then to other chains like Ethereum. So you kind of saw this before in the coding part of the API part I showed earlier, but really when you write in SnarkyJS, which is this programming language of TypeScript I mentioned, it compiles into two artifacts. For one is a prover function, which you run locally on your own device. I run it on my phone that regenerates a proof, and then a verification key, and this is what gets stored on chain, verifies the correctness of the execution of that proof. When you deploy a smart contract to Mina, what you're really doing is you're putting a verification key on chain, which says, so the account that you've attached this verification key to, now you can only update that ZK app account if you provide proofs which pass with respect to the verification key. The moment you've done this, now things are all connected up, and you can only update the account if the verification key gets valid proofs. So yeah, you can set these transactions to Mina, and Mina will check if they're valid or invalid. Little more detail here on this. Smart contract methods on Mina work as follows. You pass in method arguments, contract state, some values from the state of the world, and the outputs are updates to the state of the world and to the state of the smart contract. And the Mina itself is checking to make sure things match up. For example, the state of the smart contract is what it's supposed to be going into when the proof is submitted to the network before the update is made. It's also just normal TypeScript code. So when you write your UI code in React or whatever, you can just import the logic for your ZK app, and you can even code them all in the same project, same compilation environment. You can import things back and forth from each other. Very convenient for when you're building a UI that lives in a browser, on a phone, or whatever. It's all part of the same programming experience. Briefly on SnarkyJS, I've mentioned some things about this, so this should make sense. It's a TypeScript library. It's a smart contract language for Mina. Everything is in TypeScript, as I mentioned. So you get all these awesome tools that you're used to using just available. It's not some new programming language, new semantics or whatever. It's just stuff you're used to using. It's also very easy to learn. I don't know how easy this actually looks, but this is an example of fully recursive zero-knowledge proofs that you could use to build a recursive zk-Rollup, for example, in TypeScript. And you notice that, like, you don't have to define a bunch of like cryptographic objects and understand the implementation details of things. You get access to like the abstraction of great, I have these proofs, I want to verify them, I want to produce new proofs, I want to assert things in those proofs, and I want to then verify the outputs of those proofs. So this isn't like pseudocode, this is just literally what it looks like for building in this case, a recursive zero-knowledge proof, which produces proofs that a number is from a valid Fibonacci sequence, where you can check that in O of 1 instead of having to actually go back and compute the Fibonacci sequence to get to like the nth number. It's also very powerful. So I mentioned things like recursion, but the underlying proof system itself also is like has a lot of other bells and whistles. Besides being easy to use, the whole thing is a trustless setup. So there's no trusted setup. It's all trustless. There's also like a very cool property around how you can kind of plug in new low-level primitives into how the proof system works, kind of on the fly dynamically. I think there's like a metaphor zk-CPU we're playing with that recently there's like a blog post on that describes more how you can kind of just add new components that are very fast and efficient and zk native onto this thing through the way the proof system is designed live, which I think is it's like super cool. And yeah, so we'll take some questions. Here's some places to learn more. This is a link to like a Hello World tutorial where like you will go through building a ZK app using SnarkyJS from scratch. And here's also a link to zk-Ignite cohort 1. Like ZK apps, all this stuff, zero-knowledge proofs unlock so much new ways of building things, new ways of building zk-Rollups, new ways of building with privacy, new ways of building Web3 applications. We're currently running this like 12-week long like cohort where people are thinking of ideas, they're collaborating, and there's funding opportunities at the end. There's like good VC involvement to help get projects funded that are looking for that at the end of this. So check this out if you're interested in learning more about what ideas people are thinking of building with zero-knowledge proofs, as well as like collaborating in a community that's starting to think about, okay, what does it look like to actually deploy some of this stuff into the real world with real applications? And as I mentioned at the beginning of the talk, back here at 9 a.m., we will be live coding with zero-knowledge proofs in SnarkyJS. So if you just want to come and join and see what it's like to build with some of this stuff with zero-knowledge proofs, with TypeScript, that's going to be here tomorrow. So come back for that. And with that, I think I have 1 minute left, and I will take questions if anyone has any. I think that is okay, right? Yeah. Okay. So 1 minute, anyone has questions?
Hi, thanks for the presentation. I'm just curious in terms of gaming, what kind of use cases or applications for gaming you've seen people working inside Mina, or that you would like to see?
Yeah, so there's actually a couple particular cool ones here. I think one is fully verifiable private poker, where if you have online poker, you have this question of someone is seeing the full state of this game, and they could potentially be using that. The person running the server could be using that to communicate with someone on the side and effectively cheat on an online poker game. With zero-knowledge proofs, I think there's some work being done experimenting on this also. You can build fully verifiable private poker, so you can avoid that kind of dynamic in things like online poker. So that's at least one. There's a bunch of other ones, but yeah. Good question. Thanks. And I think that's it also on time. So thanks, everyone, and we'll see you all later in the conference. Bye.